Hey everybody, I want to show you something real quick that's kind of interesting, and this is kind of my own design based on what I've seen off of these the architecture, like the Great Pyramids, what we've seen from the crop circles. And I kind of started this when I was messing with the pyramid. As I've seen Stonehenge and some of this other architecture, I'm starting to see that this geometry is extremely powerful, because with visuals alone you can really get accurate with this stuff. So let me show you what I've done here. One of the things that I've noticed is that we have this situation, and if you remember I showed you this where you have circles that are 1/3 the size of the next one. So that, for example, this is a size 6, size 4 right here, and then a size 2 right here. So obviously this is a third. 2 is a third of 6, this is 2/3, and this is, okay. And that's the way these rings are that you see right here, okay? What we're going to do today is we're going to do this whole square and the circle thing, but I'm going to show you a different way that you've probably never seen it done before. You kind of saw it in the crop circle, but you're going to see it with extreme accuracy. And what I'm going to show you is I'm going to show you the actual calculations of the way that it should be, and then I'm going to show you what I did visually based on what I see in the diagram, and then we're going to take a look at the difference between the actual calculation and what I did. And I'm going to show you where the square is equal to the the area is equal to the area of the circle. We're going to look at the golden ratio, or that we're going to get that from a squared circle. And then the last one, which is going to be really amazing, and it's going to show you different ways to look at this thing. It kind of confirms what I was showing you with the Great Pyramid, and the way that the slopes of the pyramid and the way these circles were tangent to the slope of the pyramid. I think it all pretty much will speak for itself right here in just a second. So this is kind of what I'm doing right here. So these concentric circles that you see right here, these are just scaled half the size of the next size larger, because that's one of the things that we see. We always see that scaled by 50%. So I did it 4 times. 1, 2, 3, 4. We have 4 circles here, concentric. Then I did hexagonal circles out of that, because these in a way could be cubes, okay? And so we have 1, 2, 3, 4 towards the middle. Okay, so I'm kind of consistent with this 4, because we're kind of almost thinking of the 4 worlds here as well. And that 1, 2, 3, 4, you see that all over the place in these alchemical diagrams. So this is kind of where it's going. So this is what I'm doing. And this is the circle we're going to be looking at right here, this large circle. It has a diameter of 6,000 pixels. And that's what we're going to be working with to show everything. So let's take a look at the first one. This is where the square has the same area as the circle. And this is the way it looks right here, taken from Wikipedia. And here's the data. The correct ratio is 0.886 to 1, right? And so the diameter of the circle that we have here is 6,000. So that means the correct diameter of the square should be 5316. However, the diagram that you see up here, the diameter of my square is 5325 based on what I saw, which is a difference of 9 and a percentage difference of 0.0016, which is almost 2 1,000ths, right? So let's take a look at what this looks like. And this is what happens when you use these concentric circles. If you notice, this square is tangent. It's tangent to these circles right here, and it does that all the way down. And that kind of lets us know that we're right on the money. Now that is within a margin of 2 1,000ths by getting that right there. And by using these concentric circles in combination with these rings, that's how we get that. Now let's take a look at the next one. This next one is regarding phi, And the ratio, the correct ratio, as you know, is 1.618. The way that they get this, if we take a look at, for example, this site, the radius of the circle, okay, so is considered 1, and the diameter of the square is considered the 1.618. Okay, so just keep that in mind when you take a look at what we're doing in the diagram here. So the radius of the circle here, since the diameter is 6,000, the radius is 3,000. If we multiply that times 1.618, we get 4,854. Mine was 4,870 based on what I saw, which is a difference of 16 and a percentage difference of 3 1,000ths, which is hardly anything. And here's what it looks like. So if we zoom in, you can see these two red circles are bounding it. It's also resting on top of these two circles, and these two circles are bounding it. Okay. Now if we take a look at the square has been done at the 1.618. So if we move this down to the way they had it in the diagram, then you can see 1, right, is the radius of this whole circle, and it cuts right through the center, right? And then if we take a look at our the diameter of our square, we can see that those large ones there bound it, and that gives our 1.618. And this is within, like I said, this is within 3 1,000ths. Hardly any error at all. And you can see 4,870 and 6,000. Okay, let's take a look at the next one. Now this next one's a pretty big deal, I think. Okay, this was the one you always see with the pyramid, and the reason I've got this diagonal line going down this square like this, you'll see this in a second, but this is also used in the Kepler triangle. And so here's what it looks like. So these right here are bounding the square on both sides. So if we zoom in a little bit, and let me just give you the data real quick. So the correct ratio of the diameter of the square to the circle is 0.7855. And the radius of the circle here is 6,000. The correct diameter of the square would be 4713. And the diameter of the square you see in my diagram is 4,710. And as you can see, the margin of error is extremely low. It's like 0.0006, so that's what, 6/10,000ths of the units here. And so here's where this stuff really shines as far as being able to see what's going on here. So you can see that these circles here, how this line is tangent to it. And I've got it to where it's basically almost right on top of the lines here. Okay, so now what we're going to do is we're going to move this square to where this side of the square is on the other side, just on the other side of these red ones, and then you're going to kind of see how it all comes out here just to prove that it's correct. Let's zoom in real quick, make sure it's on those circles right. Okay, just a little bit too far. Okay, about right there. So the square is on the other side of the circle. Now here's where the magic is. So that diagonal line I was showing you, and let me just show you that Kepler squared circle real quick. So here's the one when you see the Kepler. This is phi, this is 1, and this is square root of phi. And if you notice the way that it looks here, they've drawn a diagonal line from the circle up here down to here. And if you notice there's a small gap right there, well, this line that you see right here is at 51.85 degrees that you see on the Great Pyramid. Okay, now let's take a look at mine. Mine, because of the slight difference, this angle that you see right here if you can see the angle intersects right, see this is the circle right here, so it's still right there, right? Now I want you to notice these tangents. Okay, you see the tangent that's happening here and this tangent right here. Okay, this line that you see right here of mine is at 51.75 degrees. So I'm hardly anything off compared to the Great Pyramid at all. And here's where the corner meets the circle on this side, and you can see how it's tangent to all of these guys right here. And then if we go up to the very top, this particular one right here, it's tangent to both sides of this thing. And you can see it's running tangent to all these various circles. There's something to this because this geometry is just amazingly accurate. And just to show you kind of what the Great Pyramid looks like when you put it on here, because you guys have probably seen that before, right? Let's take a look at it on this diagram. And there it is. I'm showing the blue here in order to show you the tangents of the slope, and then you can see that this right here is tangent to the slope of the pyramid also, and that the pyramid is right in the very center here, and then the point of the pyramid reaches that close, which could possibly be the difference of the 3 that I had. What is it? 6 10,000ths. But you can see it's the same thing, and you can see how all of these circles are being used in order to gain, in order to square the circle to get these various slopes and so forth. So anyways, I think there's a lot to this, and I don't know if anybody, I've never seen anybody do this before, but I think this is a pretty big deal. So anyways, I just wanted to show you guys. Y'all take care, and I'll talk to you soon.